Hello everyone. In statistics, one often encounters the situation where one needs to know the probability distribution of some statistic, the so-called sampling distribution. For example, when we compare the performance of two estimators by means of the mean squared error, we need the sampling distribution of both estimators to compute the two mean squared errors. When performing a test, we need the probability distribution of the test statistic under the null hypothesis to compute p-values or critical values. And for the construction of a confidence interval, we need the probability distribution of a pivot. In some situations, the sampling distribution of a statistic is explicitly known. For example, the test statistic for the one-sample t-test for normally distributed observations is known to have a student t distribution with n-1 degrees of freedom under the null hypothesis. In other situations, we may be able to approximate the sampling distribution. For example, for the construction of a confidence interval for the probability of success of a binomial distribution, we approximated the distribution of a near pivot by applying the central limit theorem to obtain a normal approximation for the binomial distribution. However, there are situations where we cannot determine the sampling distribution explicitly or find a large sample approximation, simply because the statistic of interest is either too complicated or because the sample size is too small for a large sample approximation. In such situations, an approximation by means of resampling may be a solution. And due to the development of computer power in the recent decades, this technique has gained popularity. In this video, we illustrate this method for a statistical problem for which explicit computation or a large sample approximation of the sampling distribution is not possible. Consider the following dataset consisting of observed inter-failure times in CPU seconds for a certain control software system. We observed failure times in CPU seconds. And the inter-failure times are the time durations between two successive failure times. We model the inter-failure times as realizations of independent random variables x1 up to xn with the same model distribution. And let capital F be the distribution function of this model distribution. Now recall from probability theory that by definition, capital F of t is the probability that xi is less than or equal to t. At this point, capital F is unknown, and there is no reason to assume any particular type of distribution. However, from probability theory, we know that if a failure at each CPU second occurs with a very small probability and independently of other failures, then the failure times can be modeled by a so-called Poisson process. In that case, the inter-failure times are independent with an exponential distribution with a distribution function f lambda, which is given by this formula. Now we want to find out whether this is a good model for the inter-failure times, and we will do this by means of a goodness of fit test. The data are realizations of independent random variables with distribution function capital F. And we want to test the null hypothesis that capital F is equal to f of lambda for some lambda greater than 0 against the alternative that it is not the case. Now we build a test statistic by comparing two estimators for capital F. One under the null hypothesis, which assumes that f is equal to some f lambda, and a so-called non-parametric estimator for capital F under the alternative hypothesis, which does not assume any specific shape for capital F. If we assume that f is equal to some f lambda, then we only have to estimate the parameter lambda. Well, both the maximum likelihood as well as the method of moments estimator is given by lambda hat equal to 1 over the sample mean. And for this data set, this turns out to be 0.0015. It represents the rate at which failures occur, so about 1 to 2 failures per 1,000 CPU seconds. So the estimator for f under the null hypothesis is simply f lambda with lambda equal to lambda hat. To find a non-parametric estimator for capital F, recall that f of t is the probability that xi is less than or equal to t. And a simple way to find an estimator is to estimate this probability by the proportion of observations that are less than or equal to t. And this brings us to the following definition. The empirical distribution function of observations x1 up to xn is a function fn, and the value of fn at t is defined as the proportion of observations that are less than or equal to t. The graph of this function is constructed as follows. Let us mark the observations over a horizontal axis, represented by the order statistics. When t is less than the smallest order statistic, then none of the observations lies below t, so that fn of t is 0. When t is equal to the smallest order statistic, there is exactly one observation less than or equal to t, so that fn of t is equal to 1 over n. And if we move t to the right, the value of fn stays 1 over n until it is equal to the second order statistic. And for this t, there are 2 observations less than or equal to t, so that fn of t is equal to 2 over n. Well, I guess you get the idea now. If we move t further to the right, then every time we pass an observation, the value of n jumps up with size 1 over n. When t is to the right of the largest observation, then all observations lie below t, so that fn at t is 1, and it stays 1 when t moves further to the right. Summarizing, the empirical distribution function of a dataset is a function that lies between 0 and 1 and has a jump of size 1 over n at each observation. Similar to the histogram, it is an additional graphical representation of the dataset that matches with a graphical feature of the model distribution for the dataset. For example, the empirical distribution function for 50 points generated from a standard normal distribution, well, this will be close to the distribution function of this standard normal, which is the blue curve. And when we increase the sample size, say to 1,000, the match will get better. Just as the histogram gives an indication of the density of the model distribution, the empirical distribution function gives an indication of the distribution function of the model distribution. And therefore, if the failure times are exponential, then their empirical distribution function should be close to the distribution function of an exponential distribution with lambda estimated by lambda hat. Well, here's a figure of both estimators for the distribution function. In orange, the empirical distribution function for the interfailure times, and in blue, the exponential distribution function with lambda equal to its estimate, lambda hat. Now, as a test statistic for the null hypothesis that capital F equals f lambda for some lambda, we use the maximum vertical distance between the two graphs. This quantity, TKS, is called the Kolmogorov-Smirnov distance. The phrase sup refers to taking the supremum over all t greater than 0. Now, mathematically, there is a difference between the supremum and the maximum, but let us not go into that here. You can think of TKS as the maximal vertical distance between the estimated exponential distribution function and the empirical distribution function. Now, because both graphs lie between 0 and 1, their maximal vertical distance also be between 0 and 1. Values close to 0 are in favor of the null hypothesis that f is equal to some f lambda, and values far from 0 and close to 1 are in favor of the alternative. Well, the TKS value for the interfailure times turns out to be 0.176. Is this far from 0? Well, in order to decide this, we want to compute the p-value, which is given by this right-tail probability. To compute its value, this requires the probability distribution of TKS under the null hypothesis. Well, you can imagine that the test statistic TKS is so complicated that this is too difficult to find an explicit formula for its distribution under the null hypothesis or to find a large sample approximation. On the other hand, if we are able to generate a lot of realizations of TKS under the null hypothesis, then we know from video 5 in week 1 that these realizations should give an indication of the distribution of TKS under the null hypothesis. For example, a histogram of TKS values should be close to the density of TKS. And similarly, the proportion of TKS values greater than or equal to 0.176 should be a good approximation of the p-value. Now, because under the null hypothesis, capital F is equal to an exponential distribution function, to generate one realization of TKS, we start by generating a sample from an exponential distribution. Then compute the estimated lambda hat for lambda and the estimated exponential distribution function. And next, compute the empirical distribution function of the generated sample and then compute the Kolmogorov-Smirnov distance. The only question that remains is from which exponential distribution should we generate the sample in step 1? Well, on the basis of the observed interfailure times, the natural candidate is the exponential distribution with lambda equal to its estimate, which is 0.0015. So this leads to the following resampling scheme. We generate a new dataset of interfailure times from an exponential distribution with lambda equal to 0.0015. And for this new dataset, we compute the Kolmogorov-Smirnov distance. And finally, we repeat this a lot of times. And the more repetitions, the better will be the approximation. We choose 1 million repetitions. This takes about 2 minutes due to the complexity of our test statistic. Now here is a histogram of the 1 million TKS values. It gives an indication of the density of TKS under the null hypothesis, which appears to be skewed to the right. The 1 million generated TKS values can also be used to approximate the p-value corresponding to 0.176. And we do this by computing the proportion of TKS values greater than or equal to 0.176. It turns out that only 2 TKS values are greater than 0.176. And therefore, the approximated p-value is so small that we reject the null hypothesis. We conclude that the distribution of the interfailure times is not exponential. Now, the resampling scheme to approximate the distribution of the test statistic is called the bootstrap. And because under the null hypothesis we generated the new datasets from an exponential distribution, which is characterized by a parameter lambda, it's called the parametric bootstrap. The situation becomes more complex if there is no particular parametric probability distribution to generate from. An example of such a situation is discussed in the next video. See you then.